All right, so here we are, week 3. We're going to talk about, to talk about iterative methods in our iterative methods class. We're going to talk about 3 methods this week. I'm going to give you the algorithms this week, and then next week we're going to analyze those algorithms, which means things like under which situations they converge, the approximate runtime, all of this stuff. And so next week is where we're going to bring back and even add to some of the linear algebra that we did in the first week. Okay, so it'll be a very mathy week. I'm excited about both of these weeks. I think the material in the whole class is great, but I think these 2 weeks are especially exciting because it's when we're first looking at iterative methods. So the 3 methods that we're going to learn, Jacobian, Gauss-Seidel, and successive over relaxation. Now probably only that last one is something that would even be called, would be something that gets used today. The first 2 are not going to be used, really, practically speaking, because there's other things that are faster. However, I'm not just going to teach you the SOR, because the successive over relaxation, because there's a very natural progression to go from the Jacobi method to the Gauss-Seidel method to the over relaxation method. They're just very natural, sort of like, oh, we do Jacobi. What if we modify it a little bit and do it this way? Okay, we have this. What if we modify it a little bit and do it this way to get us the SOR method? So it's really good to know where all of these come from. Otherwise, you're just getting a formula. And then it's good also to understand why different methods work better than others. Anyways, okay, so in this video, I'm going to tell you the Jacobi method. In all of our things, we're going to be solving equations of the form AX is equal to B. Now, the assumption here is that B is known, obviously, and X is the unknown. That's what these things typically mean. And A is going to be a matrix. Now, the algorithm that I'm describing here is going to work for any A. As long as A is a square matrix, the algorithm that I'm describing is going to work. Okay? No matter what A is, as long as this is a square matrix. But in our minds, we're thinking about applying this for sparse matrices, because we're going to have to, as you're going to see, you're going to have to do many multiplications of A times different things. And so if the matrix isn't sparse, that takes a long time to do. So the algorithms that I'm going to write work no matter what A is, but we're really only going to apply them to sparse matrices. Okay, so we have AX is equal to B. What we're going to do is we're going to guess at what the solution should be. We're just going to take a guess. And we're going to call this X sub 0, or X super 0, is a guess at the solution. Okay, it's just a guess. I don't know. Put your kids' birthdays in it or something. Just a guess. Typically, we'll use the 0 vector, but it's just a guess for what the answer should be, for what the solution is. And now we're going to compute something, as we've seen before, called the residual. The residual is going to be equal to AX, 0 there, AX minus B. It's just a vector that gives you the error, okay? X naught is our guess. This is the residual. It's kind of like the error between it's not the error between the actual answer and our guess. It is the sort of maybe the more important error, which is how far we are from our solution. Okay, so R0, and in general, we're going to have different indices there, and that index there will change. Okay, so now what we want to do is I want to say, okay, my goal here is to make all the entries of this vector 0. So how can I modify my guess to try to make these entries 0? So this is what the method, one of the ways we can sort of think about how the method is based. Well, what this means then is that for every k, if I want to do this, then I'm going to have for 1 less than or equal to k, less than or equal to n. So we're assuming that A is an n by n matrix. And unlike Python, we're going to start our index at 1 rather than 0. So for 1 less than or k less than or equal to n, I want to have the kth entry of my residual vector to be 0. So I want to have 0 equals RK0. And what does this mean over here? It means this is equal to 0. So what is this going to be? Well, I'm going to have minus the kth entry of B. So I just need to compute the kth entry of this vector here. So I'm going to have the sum, let's say J equals 1 to n a kj. So it's the kj a kj. The row, it's a kth row. The columns are changing times a0 j like that. So I want this to be true. Now, if I look at this equation, I can solve it for x. I can solve it for what xk should be. So if I take this equation and I solve it for xk, okay, it's going to tell me that xk0 is going to be equal to the kth entry of b. Let me start it like this: akk times the kth entry of my vector is going to be equal to the kth entry of b. I'm just moving this over here minus this sum. Okay, but I'm not solving. I moved the xk over here, so this sum no longer includes the term where j is equal to k. So we're going to have j equals 1 to n, where j doesn't equal to k, and then we're going to have a kj xj0. And then if we divide both sides by akk, we're going to get something like this. We're going to get something like this, okay? Now, what this says is that if we make, in our new vector, if we change ak so that it's equal to that, and keep all the other entries the same, what this tells us is that r in the kth entry is going to be equal to 0. Okay, so instead what we do is we're going to define ak1. So this is the 0th guess. xk1 is now going to be this guess, and it's going to be this right here. It's going to be given by this formula for every k. So we're going to update all of the k's, and we're no longer going to have the case where, you know, one of the entries in the residual vector is equal to 0, but the idea is that we're moving in the right direction. And if we do this process enough times, the residual is going to go to 0. So let me show you another way that we can think about this. So we can write our matrix A in the following way. I'm going to do this a little bit different than how the book does it, simply because when I tried, it's a little embarrassing, but the book has too many minus signs, and when I tried to write out my lectures, I got confused with the number of minus signs. Sorry. So we're going to call this is going to be the upper triangular part, this is the lower triangular part, and then there's the diagonal part. Okay, so then A is equal to U plus D plus L. So A is equal to U plus D plus L, and then I'm just going to define R to be equal to U plus L. So this is going to be equal to D plus R. In other words, I'm saying R is equal to U plus L. Okay, so we have our matrix. It's the diagonal part, and then everything else. Okay, now this actually suggests something about why this method is going to work. And one of the reasons is, as we will look at next week, the matrices are going to be called diagonally dominant. So in some sense, it's like the diagonal is the main part. So if we rewrite the matrix vector equation, we're going to have D plus Rx is equal to B. Okay, if we rearrange this, this becomes dx is equal to B minus Rx. And now when we're talking about iterative methods, and we can set up a system like this, essentially what this does is that it suggests that this should be the thing that tells us what the iteration scheme is. So in other words, if we look at, say, our guess, like if x0 is our guess, we're going to have something like this, and then we're going to define the next iteration in our method to be something like this. And in general, we're going to have something like this. And then this is going to be our sort of way of deriving an iterative method. Now, D is a diagonal matrix. We want to know what xk plus 1 is. D is a diagonal matrix, so it's very good here. We can divide both, or we can multiply both sides by the inverse of D. And since it's a diagonal matrix, that's something that's very easy to do. We're going to get D inverse times B minus RXK. Okay. And so we're going to define our iterative scheme this way. And typically we'll start x0 will be the 0 vector, and then this is what, x1 is going to be this. X1 is equal to this, but with the 0 vector, that gives us a new x1. X2 is going to be this, but that's x2. Okay, well, we can always, take something like this, just define an iteration scheme. The question is it going to converge? And if it does converge, is it going to converge to the solution? Okay, so like I said, next week we're going to show that this method converges. But let's just think about this. Let's just imagine that this method does converge. Okay, in other words, let's say if I do this over and over again, the sequence of xk's is going to converge to some vector. Okay, what's going to happen then? Let's say that vector that we call it is x star. Let's say it converges to x star. So if I take the limit as k goes to infinity on both sides, it's going to converge to x star here. And on the right-hand side, we're going to have D inverse B minus R x star like this. Okay, so if I multiply both sides by D, I'm going to get this. If I add R times x star to both sides, I'm going to get D plus R x star is equal to B. But D plus R is just A, and so this equation says A times x star is equal to B. So what it says is that if AK converges, if the sequence defined this way converges to a vector, that vector is going to be a solution to this equation right here. Okay, so this is the basic Jacobi iterative scheme. In your first homework problem, you already programmed this. So you've already seen something like this before, and you've seen that it works. Like I said, this is not a method that gets used very often in practice, or probably at all in practice. We're going to look in the next video at another method called the Gauss-Seidel method, which is a slight update of this method, and that method also does, it sounds like I was about to say it does get used. That method probably also does not get used. And then after that, we're going to look at successive over relaxation, and that is something that's more likely to be